afternoon, everyone. I'm Catherine Brookman, Associate Director, Knowledge Transfer and Exchange, and on behalf of Dr. Jack Callahan, Director of the Center of Research Expertise for the Prevention of Musculoskeletal Disorders, or CRE-MSD as we are more commonly known, we'd like to thank you for joining us today for this free webinar. We are grateful to the Ontario Ministry of Labour, Training and Skills Development for our funding, which supports the delivery of these webinars, and to our presenters who provide their expertise. We ask that you keep yourself muted for the duration of the webinar. To mute yourself, please use the microphone icon in the control panel that appears near the bottom of your screen. When you are muted, the microphone icon will be the color red. The format of today's webinar is as follows. I will briefly introduce you to our speaker. The presentation will be given, after which time we will have 10 to 15 minutes for your questions. We ask that you type your questions using the chat feature, and I will relay your questions or their themes should there be duplications to our presenter for him to respond to. You can view and use the chat feature by selecting the chat icon in the control panel that appears near the bottom of your screen. The chat window will then be displayed on your screen. We also ask that you use the chat feature to communicate during the webinar. Should you have a pressing question that cannot wait until the end of the presentation, such as a technology glitch, please type this into the chat window, and we will do our best to address it right away. We will be providing you with a copy of the presentation shortly after the webinar, along with an evaluation that we encourage you to complete, as this will assist us in the future delivery and planning of our webinars. The webinar is recorded, therefore we ask that you keep yourself muted for the duration of the webinar. Thank you again for joining us, and now it is my pleasure to introduce you to our presenter, Dr. Peter Johnson. Pete is a professor in the Department of the Environmental and Occupational Health Sciences School of Public Health, University of Washington. He and his lab are internationally recognized for their work evaluating seating alternatives to reduce vehicle operator exposures to whole body vibration. Currently, in cooperation with multiple universities, his lab is conducting studies to evaluate ways to reduce whole body vibration exposures in the semi-truck, bus, and mining industries. Dr. Johnson is a member of the American National Standards Institute's Whole Body Vibration Committee and an American delegate on the International Standards Organization Whole Body Vibration Committee. In addition, he has worked with Microsoft, Hewlett-Packard, Logitech, assisting with the design and evaluation and introduction of new tablets, notebook computers, keyboards, and mice, and with Steelcase on the design and introduction of new ergonomic office furniture. Thank you, Pete, for agreeing to present today on adverse outcomes associated with occupational exposures to whole body vibration, making a health, safety, and business case. Over to you.
All right, Catherine, thank you for that introduction. And I would like to pride myself in that I'm near Canadian. I have lived in states bordering Canada most of my life, and I speak Canadian English near fluently. And I want to thank CRE-MSD and the University of Waterloo for the opportunity to present. And now let's see if I can get my slides to go forward. There we go. What this slide shows is the incident rate for occupations with 20,000 or more injuries and illnesses from the Bureau of Labor Statistics. And you can see vehicle operators are at the top of the list. And on the right side here is the incidence rate per 10,000 full-time workers. And that vertical line is the average across all industries. And you can see these industries with a high number of injuries also have high incidence rates. So I think professional vehicle operators are a highly exposed group, both in numbers and for the incident rates with injuries. This is some work that's been done by the Washington State Department of Labor, the SHARP group, and they have a trucking injury reduction emphasis and safety program, which has done great work. And this is from one of their publications. And the vertical red line is showing the average injury rate across all industries in Washington State. And you can see in the trucking sector, their injury rates are anywhere from 3 to 6 times or 3 to 4 times higher. What this slide shows is where claim costs are going. And the single largest component, over 40%, is for musculoskeletal disorders. And if you look at an average claim in the trucking sector with days away from work involved, where the worker is out 3 or more days, the average cost of the claim is $30,000 US. And on an annual basis, that is costing Washington almost $250 million in claims costs. And obviously, it's going to be billions of dollars when you consider the United States and Canada. Whole body vibration is associated and has been associated with low back pain and low back pain development. Back injuries are the most significant non-lethal medical condition in North America. Epidemiological studies have consistently linked whole body vibration to low back pain and injury. And from what we do know, there is a dose-response relationship where typically it will take 5 years or more for these problems to develop. So they're truly a cumulative trauma disorder where it's an accumulation of trauma over time. So what the heck is whole body vibration? Well, I'm an engineer, and what is nice is whole body vibration is an objective measure to describe vehicle operator motion. It's a vectored quantity, so it has both the magnitude of the motion and the direction. And to characterize whole body vibration exposures, we use 2 parameters: the frequency of the exposure, how often the person or the vibration oscillates up and down or side to side or fore and aft, and acceleration, the magnitude of that motion, which is in meters per second. And what we typically do is we put a seat pad accelerometer on a seat that measures vibration in 3 directions. And we measure the vibration up and down in the z-axis, side to side in the y-axis, and fore and aft in the x-axis. And we look to see if there's a predominant axis for the exposure. And if there is a predominant axis, we usually focus on that axis for health outcomes, but that does not mean the other axes are not important. So how does vibration affect humans? Well, we have very low frequency vibration, which causes motion sickness. That's below 1 oscillation per second. For hand-arm vibration, it's much higher frequency, anywhere from around 8 to 1,000 oscillations per second. But for whole body vibration, the problem is predominantly between 1 and around 20 hertz, between 1 and 20 oscillations per second. And if those of you who live in the US and had a physics class, you're probably taught about Galloping Gertie, which was a suspension bridge in Washington State. And this is a really nice example of why the frequency of the vibration or the energy is important. And basically what happened is when the energy content matches the natural frequency of the structure, it makes the structure do things otherwise it would normally not do. So for example, when vibration matches the natural resonant frequency of your spine, which is somewhere between 6 and 12 hertz, it makes your spine move and oscillate in ways it usually does not do. So as far as frequencies of concern, We're primarily concerned with the spine, and it has a resonant frequency of anywhere really between 6 to 12 hertz. Vibration can affect your digestion and reproductive organs. So your digestive system, your stomach, and its organs resonate between 4 and 10 times a second, and your shoulders oscillate between 4 to 5 hertz. So we're primarily concerned with frequencies between around 4 and 12 hertz for musculoskeletal exposures potentially related to and exacerbated by whole body vibration. So this shows a causality map, and what I would like you to believe is that there are certain seat types that can impact whole body vibration and affect low back pain. They're industry standard seats, and we're starting to see enhanced seats that are available. So one of the things I'm interested in is whether seat types can help reduce whole body vibration exposures and have an influence on low back pain. So I want you to think about being a commercial vehicle operator and having your choice between 3 types of seats. Back in the 1950s, we had these suspensionless seats where the pedestal was height adjustable and foam was the only means of protection. Then in the 1960s, we started to get these suspension seats with mechanical springs that would move up and down and provide some protection from the vibration along with the foam seat. And then in the mid 1980s, around 20 years later, we finally got these air ride seats where you're riding on an air spring and in theory, a cushion of air. So just imagine being a commercial vehicle operator, and I want you to choose a seat that you would want in your vehicle between these 3 seats. So one of the challenges with these suspended seats is sometimes if the operator is too heavy or if the suspension is underdamped or worn out, they can amplify the exposure. And this is a video of a person in a bus going down a mundane freeway in Seattle over an expansion joint. And I don't even notice this expansion joint in my car. I go over it driving to the airport. But you'll see in a bus with a very stiff suspension, it's a little bit different animal. And it looks like I have to turn my cursor off. So watch this person going to the next And there was supposed to be a cursor going across, which didn't show up, but this is when the person bottomed out on their seat. And the next one is right here. So the red line is the vibration or acceleration we measured at the seat, and the black line is what was measured from the floor. So that seat amplified the vibration exposure by around 3-fold, just due to being underdamped. So there are some challenges with these suspended seats, and I say passive suspension seats, meaning either mechanical or air suspension seats. When you're driving, you hope to have a magic carpet ride, the straight trajectory, but what happens is you go on a bump, you experience a jolt, and you come out of the bump and experience a jolt. And rather than a magic carpet ride, the suspended seats can amplify these exposures if you're traveling at moderate to high speeds. For off-road vehicles, due to the slower speeds, this amplification is not a problem. So the first thing I would like to convince you is that seat suspension design matters. And this is a study we did almost a decade ago looking at whole body vibration in bus drivers in the Seattle area. And what we did is we had a 6-year-old 40-foot or 13.3-meter bus and 15 subjects, and we had a 6-year-old air ride seat, and we took these drivers on and created a standardized route in the Seattle area where they had around 7 kilometers of stop and go on city streets, around 9 kilometers on a freeway, a kilometer around some speed humps at a community college, and again, 7 kilometers going down an old tired freeway with expansion joints. And actually, the results I'm going to show you are from a relatively new and fresh seat, but it was going over this route. So when we took the drivers on this route, what this slide shows is the percentage of the floor vibration reaching the operator. So where you see red on this map, the seat is amplifying the vibration exposure. Where you're seeing orange, what that means is 90% of the floor measured vibration is reaching the operator. And when you see yellow, which there's not much of, that means 70% of the floor measured vibration is reaching the operator through their seat. So on average, with this air suspension seat, 88% of the floor measured vibration reached the operator, meaning the seat reduced the floor measured vibration exposures only by 12%. So I was a little bit surprised by that, and I didn't know if that was typical. But we've since measured other air suspension seats in buses and trucks, and we typically see them reducing the vibration exposure anywhere between 5 and 25%, with the majority of the seats just reducing the exposure between 5 and 15%. So then what I did is I had work in Northern Europe, and for some reason, they had a 1950s height adjustable static seat in some of their buses. And I was able to get 2 of those seats shipped over, and using the same bus and the same route and the same drivers, we put this static suspensionless seat in our bus. And to my surprise, it amplified the vibration a greater percentage of the time. Roughly 70% of the time, 90% of the vibration was making it through the seat. But here we see that there's more yellow, that around 20% of the time, only 70% of the vibration was making it through the seat to the operator. So here we have a suspensionless seat, and it almost had the same amount of vibration reduction as the air ride seat, 12% for the air ride seat and 11% for the suspensionless seat. So that started to get me to scratch my head and wonder, well, what the heck's going on? So take-home message from this is I'm wondering if the current air suspension seats are not optimized for on-road vehicles. And maybe these long travel suspensions in these on-road vehicles aren't needed. Typically, the perturbations or the terrain you're going over after the tire and the suspension has got to them, typically you need less than probably 4 centimeters of suspension travel to get rid of the vibration. So in 2010, we were kind of thrown a curveball. Of all companies, Bose Corporation has come out with an air suspension seat. I'm sorry, an active suspension seat. What they did is they took their sound canceling technology and they applied it to a truck seat suspension. And what this suspension has is a linear electromagnetic motor, and it looks at the vibrations coming to the operator, and it tries to cancel the vibration out. Here's an example showing the video of a person on the left sitting in a regular air suspension seat and the person on the right sitting in the active suspension seat. And they're going to be simulating a washboard road. And you can see, I think this is the manager. He looks pretty cool and calm. This might be a subordinate. And you see a little bit of difference in shaking in the torso. Then they're going to lift their feet up, and a little bit different in the shaking in the feet. And I don't know if they adjusted for coffee consumption when they filmed this video, but obviously you can see differences of shaking in the upper extremity. So this was pretty interesting to us. The seat is like an air suspension seat. It has an air spring, but what's different is it has a sensor to measure the vibration coming up through the seat and a computer processor. and then it uses the linear electromagnetic motor to cancel the seat vibrations out. So what we did is we tested these seats in a group of 16 truck drivers. We got 2 identically designed trucks. We put the air ride seat in one truck and the air suspension seat, the air ride seat in one truck and the active suspension seat in the other truck. And we had the trucks drive on the standardized route. The truck drivers would switch trucks and drive on the same standardized route again. After 8 drivers, we switched seats between the trucks to make sure that there wasn't an effect of the truck suspension, and we completed these measurements with 16 truck drivers. And this is just showing the standardized route which they drove over. Basically, you can see this is the results from the air ride seat. And again, you see the vast majority of this time, 90% of the vibration is making it through the seat suspension to the vehicle operator. So in this brand new air suspension seat, roughly it was attenuating or reducing the vibration by only 5%. So this is kind of our second instance in showing the amount of protection from some of these air suspension seats. And then with the active suspension seat, you see something completely different. The majority of the time, almost 90% of the time, only 30% of the vibration is making it through the seat to the operator. So on average, this seat is reducing the vibration exposure by 64%. So the amazing thing is usually when we see engineering controls, we see an incremental improvement. But this active suspension seat rendered this semi-truck to basically ride like a luxury car. But the challenge is these active suspension seats are expensive. A typical air ride seat is going to cost you anywhere between $600 to $1,200, depending on the brand and model. And active suspension seats are more expensive, anywhere from $4,000 to $6,000. So there certainly is a price differential. So next, what I'd like to present is we did a study of this active suspension seat and comparing it to an air ride seat. We did a randomized controlled trial with a group of 20 truck drivers in each arm where they were given a seat, and for a year we measured their vibration exposures and low back pain outcomes over that 1-year period. Here's our study design. We started out with 80 drivers, and what we did is we got 40 drivers with low back pain. They had to have low back pain to participate in the study. 20 were randomized to receive a new air suspension seat, and 20 were randomized to receive the active suspension seat. We measured vibration exposure before they got their new seat, and 3, 6, and 12 months after they got their new seat. And we also measured their low back pain before they got their intervention, and 3, 6, and 12 months after getting their seat. So here are the results for the 2 groups. The control group with the air suspension seat is the light bar with triangles, and the intervention group is the dark line with squares. And this is the vibration we measured from the floor of the vehicle. The red line is the ISO lower level health caution guidance zone, or EU action limit. So you can see the vibration we measured from the floor of the vehicles were below the action limit. But what is also good is there is no difference in exposure between the 2 groups as far as the truck measured vibration. It didn't change pre-intervention. PR is pre-intervention. This is post-intervention, 3 months post. And then we combined our 6 and 12-month measures just due to a large number of dropouts. So there's no difference in exposure between the 2 groups, which is the good news as far as floor measured vibration in their semi-trucks. Now here are the results from the seat measured vibration. And when we replaced their old air suspension seats with either new air suspension seats or the active suspension seats, we saw a significant reduction in their vibration exposure. So this just indicates that probably after time there could be some benefit of even just replacing old air ride seats with new air ride seats. But there was a more substantial reduction in the vibration with the drivers that received the active suspension seats. So on average, after putting in the new seats, 85% of the vibration, floor measured vibration, reached the drivers with the air ride seats, and only 57% of the vibration, floor measured vibration, was transmitted to the drivers having the active suspension seats. So on average, a 15% reduction in vibration for the air ride or control group, and a 43% reduction for the active suspension group. What this shows is how long one could drive before reaching the action limit. So since the exposure with the original seats was lower than the action limit, you could drive 10 hours before exceeding the recommended exposure in the ISO or EU standards. With the air ride seats, with the new seats, they could drive 16 hours a day. And then with the active suspension seats, they could drive 34 hours a day, or the speed of light. And I'm not advocating people drive this long, but it just shows the impact of the reduction of the exposure. This is a kind of a linear scale, but the effect of the vibration is on a logarithmic scale. So there's a very substantial reduction with the active suspension seats relative to the new air ride seats. So here are our low back pain results, pre-intervention, 3 and 6 months post. And this is their average level of low back pain on a 0 to 10 point scale. So lower is better and higher is worse. And it doesn't look like a whole heck of a lot, but there were differences in the baseline level of low back pain. And then when we adjusted and looked at the change in low back pain relative to baseline, we did see some differences between the groups. Both groups, once they got their new seats, reported a reduction in low back pain. And what's important is a 25% change in self-reported low back pain is considered clinically meaningful. And then 6 months post-intervention, low back pain was still lower for the active suspension seat, but approached baseline levels for the control seat. And part of the challenge with this study is it was underpowered. We only had 20 drivers in each group, so this wasn't significant. But what is interesting are the trends after getting the seats and the difference between the two groups in the self-reported low back pain, which appears that it may be related to the differences in exposure. Here are other things that we measured. We measured physical function with an SF-12 questionnaire, and we saw lower is better with these physical function. This is low back pain disability and a physical composite score. So here on these two, lower scores is better. There were, higher scores are better. So drivers with the active suspension seat reported having slightly greater physical function and a measure of physical feeling with the composite score. Lower is better on this side, so there's a slight difference with reporting less disability, and also they reported having better sleep when we looked at sleep and pain interruption. None of these reached significance, but again, the trends in differences were interesting to us because they somewhat corroborated with the difference in exposure between the two seats. So here's kind of my take-home message. I'm a golfer. I'm not a very good golfer, but 0.5 meters per second squared is the average level of exposure that's recommended for 8 hours according to the ISO standard and the EU regulations. And I consider that to actually be double bogey because our drivers had low back pain and their exposures were below that recommended action limit. with the drivers that received the new air suspension seats, and we reduced the exposure to around 0.35 meters per second, I consider that bogey. We did reduce their low back pain, but it wasn't as substantial as with the active suspension seats. And with the active suspension seats, if we reduce their exposure to 2.5 meters per second, we saw a clinically meaningful change, 3 months intervention, and a change 6 months, but we saw a greater reduction. So I'm wondering if really around 0.25 meters per second might be par as far as exposures. And I'm wondering if this 0.5 meters per second squared is not protective enough. So that's my thoughts on the vibration exposure levels. Next, what I'd like to do is get into the cost aspect of vibration exposures. And this was a study done by mine, Kat Gregerson, and other co-authors, where we assessed the cost and health effects with different seats. So what we did is we did what's called a cost utility analysis, and we looked at 4 different scenarios, and this was with the bus fleet at our bus municipality, King County Metro, where they employ around 3,000 drivers and have a 1,500 bus fleet. And we wanted to look at, by looking at claims costs, the costs of 4 scenarios. One was their existing scenario, where they keep the seats in the buses over the 15-year life and periodically maintain them. Another scenario was looking at replacing the seats every 5 years, thinking they get worn out, and putting in new seats could be beneficial. Another was looking at static 1950s vintage seat, showed that its exposures were no different than the suspended air ride seat. And then we also looked into putting an active suspension seat, the same one that we used in the truck study, which has been shown to reduce the whole body vibration exposures by 50% or more, or almost double of what the air ride seats do. So we developed a Markov model for this study, and basically looking at 15 years of claims, which is the life of which they keep a bus for King County Metro, and they keep the bus 15 years so they can totally depreciate the cost of purchasing the bus. As people could go from a well state where they're healthy into either an acute injury, a subacute injury, or a chronic injury. And we looked at neck injuries, back and neck injuries, and just back injuries. So people in this model could cycle through based on claims between these various different states. And basically what we found out is the majority of the injuries were just acute injuries, or shorter term in duration. And the majority of the injuries that we were found were in the low back. And as you can see, roughly 3% of the time people were in an injury state, and 97% of the time they were in a healthy state. And if you look at the point prevalence of low back pain on any given day, when you look at a population, roughly 10% will have a low back injury. So I'm wondering if we really underestimated the amount of low back pain, and that could be possible because not everybody files an occupational health claim with an injury. Okay, so a definition of an acute injury is one that is less than 3 weeks. Subacute was 3 weeks to 3 months, and chronic was greater than 3 months. So taking this actual claims data, we were able to get the actual claims costs. So on average, an acute injury across all locations cost on average $3,800. A subacute injury costs $15,000 per claim, and a chronic injury on average $100,000. So inputs to the model were the costs. With the existing scenario, there's a purchase price of the seat, plus $950. They replace the cushions and the shocks every 5 years. For the static seat, it's lower in cost, and we estimated a lower maintenance cost just replacing the cushions since there are no shocks to replace. And the active suspension seat, higher cost, and we assume the same maintenance cost every 5 years. And then the last scenario was buying a new air ride seat in years 5 and 10. So there's 3 seats, so that had a cost of $6,400 and no maintenance costs. Part of the cost utility analysis is I say it's like a complex number. There's a real component to the complex number, which is the cost. And then there's an imaginary component, which really isn't imaginary. They look at the health utility of the worker. So there's kind of 2 dimensions. And we use these utility inputs into our cost utility analysis. So looking at this population based on age and pain, they had a utility of 0.67. So when we're born and pain-free, we have a utility of 1. But as we age, we slowly develop pain, so our utility goes down. And then we looked at the savings, and with the existing, there's no savings. That's what's being done currently. With the static seat, there's $650 in maintenance savings over years 5 and 10. With the active suspension seat, we assumed, based on the reduction of low back pain from our truck study, that there'd be a 15% reduction in low back claims where people would be in a well or healthy rather than a claim state. And for the seat replacement, we said that we estimate there would be a 5% reduction in people being in a claim state. So those were our assumptions with the model. So here are our costs for each of the scenarios. And this is actual cost using claims. So over 15 years and 1,500 buses in King County Metro, and they're on average 3,000 employees. On average, over that 15 years, $28,000 in claims would occur with the existing seat. Since there's no difference in vibration exposure, the same amount of claims would occur with the static seat. With the active seat, there's a 15% reduction in claims, so the claims cost is lower. And with the seat replacement, we estimated a 5% reduction in claims, so that cost is slightly lower than the existing. So here are the total costs. Here's the total costs and injuries over the 15 years for their fleet. And you can see that the static seat would save them through reduction in maintenance costs $2 million. The 15% reduction in claims over the life of their fleet would save them $4.5 million. And the seat replacement did not prove to be cost effective. The additional purchasing of the seats outweighed the reduction in claims, and they ended up costing them $2.5 million. So this is what a cost utility does. One axis is the cost of treatment being more costly in the x-axis positive and less costly negative. And then there's this quality adjusted life years or utilities where their health or quality of life improves using the x-axis to the positive, or your health quality goes down. And you have 4 quadrants. If it is higher cost and their health goes down, you definitely don't want to do it. If their quality of life improves and the cost goes down, this is a green area. It's a great decision. Where it's a little bit indeterminate, if the cost increases and the health increases, it depends on the trade-off between the two where you may want to do it. And if the cost goes down and their health decreases, again, it's indeterminate. So that's how the cost utility analysis works. And here is our outcome. With the existing scenario, you're at the center of this cost utility analysis because that's current condition. With the seat replacement, it costs more, and it also improved the health. So it's in the yellow area. It's somewhat dependent on the trade-off between the two. With the static suspension seats, there is no change in health, but it reduced costs. So again, it's kind of in an indeterminate area where it depends on the trade-off between the two. And then finally, with the active suspension seat, it improved the quality of life and it reduced the costs. So that would kind of indicate that the switching to active suspension seats appears that it may be favorable from a health and business perspective, given that it improved health and reduced claims costs. So in summary, this showed that the active suspension seat appeared to be cost effective, saved around $4.5 million. And we could do a sensitivity analysis and it would be cost effective all the way down to just a 5% reduction in whole body vibration related claims. The static seat was cost effective. It saved in maintenance costs, but would not reduce claim rates. And I would imagine unions would not be too happy to take their suspended seat and putting in a non-suspended seat. And finally, the frequent seat replacement was not cost effective. All right, now what I'd like to transition to is talking about safety in trucking. Because not only can there be musculoskeletal injuries, but there can be accidents associated, fatigue-related accidents. And the first thing I would like to present was a wonderful study done by Bronson Dew, Phil Bigelow, and other colleagues at Waterloo, looking at the impact of whole body vibration exposure on driver reaction times. And now what we're looking at is this part of the causality map, where whole body vibration can lead to driver fatigue. Perhaps that affects their reaction time or vigilance, and maybe that could contribute to accidents. So there can be savings from musculoskeletal disorders and also savings by reducing accidents. With respect to truck drivers and fatigue, 47% of truck drivers have reported falling asleep. And in past studies, a quarter have reported doing it within the past year. The cost of vehicle crashes is significant. The average claim cost when there's a crash involving a truck is $91,000. And if there's a fatality, you're looking of upwards of $3 million in crashes. So these crashes, while there may not be that common, if there are fatalities involved, those can often far exceed the musculoskeletal costs of these driver-related injuries. So now I'd like to introduce what we use, which is something called the psychomotor vigilance task. It's a sustained reaction time task where we measure the response times of people to stimuli that are randomly presented. So every between 2 to 10 seconds, a stimuli is presented and they have to react to it, and we measure their average reaction times. And it's kind of the gold standard for alertness, and it's really commonly used in shift work, measuring the effects of different work cycles on fatigue. And it's reliable and valid. So dependent variables in the study, we measured whole body vibration from a group of truck drivers. We measured their reaction time task, and this is how it was actually performed. There's a computer screen where the numbers start scrolling, and once the numbers scroll, they push the space bar, and we measure their mean reaction time, their 10% fastest reaction times, and if it takes longer than a half a second, that's considered a lapse. And also measured pain in various body regions on a 10-point scale. So this was a very small study. We had 5 truck drivers, and due to logistical reasons, we couldn't randomize seat presentation. So what we did with these truck drivers is over a 1-week, 5-day work period, We measured their whole body vibration exposure the first day, and we measured their reaction times at the beginning and ending of the day over the 1 week period. Over the weekend, they were given an active suspension seat, which we knew substantially reduced the whole body vibration exposures. We measured their vibration exposure and then their reaction times beginning and end of shift over their full day for 5 consecutive days. So here are the results. This is looking at reaction times pre and post shift, and with the passive seat and the active seat. And basically what we found out is pre and post shift, the reaction times increased, but they increased less with the active suspension seat. So we did see a significant difference where there was less of an increase in the reaction times in the drivers that received the active suspension seat compared to the passive suspension seat. And this, you can see the trend over time across the seats, the dashed line being the passive seat and the solid line being the active seat. So interesting, it looks like there could be potential where there's differences in reaction times in this small sample between the two seats. And then we also looked at the 10% fastest reaction times. And the thought being is that it's hard to improve on your fastest reaction time. And if there is some effect on your fastest reaction time, that's also meaningful. So we also saw a significant difference in their responses with the fastest reaction time. So somewhat encouraging to us that there may be differences in reaction time between these truck drivers when given a regular passive or active seat. This was also very interesting when we measured their discomfort pre-shift and low back pain and post-shift over the course of the day. With the drivers that received the passive seat, there was a substantial or significant increase in low back pain, where those with the active seat, there is no real change in low back pain pre and post shift. So also some potential effect subjectively on the amount of low back pain these drivers perceived pre and post shift. Next, I'd like to do this.
We have about 4 minutes.
4 minutes, all right.
Okay.
So next, I want to compare a field study comparing psychomotor vigilance tasks and another study comparing 4 seats. And the objective here was similar to Bronson's study, where we wanted to determine if there's changes in response times pre and post shift with whole body vibration exposure, and whether different seats affected the reaction times. So we used 4 seats in the study. One was their existing seat, and then we evaluated 3 aftermarket seats, 2 being passive seats and the other being the active suspension seat. This was what the truck drivers drove on was a route that lasted 11 hours, and it was a standardized route where they went to a mine, picked up aggregate, returned it to the ocean, and then went back to the base. And here is the vibration exposure that we measured from the different seats. It was a repeated measures design, but not all of the drivers could repeat the measurements. But we did see significant differences in vibration exposure between the 4 seats. This is the action limit. They're slightly over the action limit with their existing seat. The 2 aftermarket seats seem to perform better, and we see our typical exposure with the active suspension seat cutting it in half. And this is the amount of vibration transmitted from the floor to the vehicle operator. So almost all of the vibration made it through the seat to the operator with their existing seat. Roughly 10% reduction with seat 2, a 15% reduction with seat 3. And then again, you're seeing around over a 60% reduction with the active suspension seat. This shows how long, based on those exposures, you could drive. And if you're above 0.5 meters per second, you would have to operate the vehicle less. So these aftermarket seats reduce the exposure below the action limit so you could drive longer. And again, very large difference with the active suspension seat. So when we looked at our reaction time results, we saw one effect with the existing seat, and we saw a different effect with the 3 enhanced seats. Well, we combined the effect from the 3 enhanced seats. And again, we did the reaction time task, and these are our results. So for the original seat, we saw an increase in the reaction time. And with the enhanced seats, we actually saw a slight reduction in mean reaction time. So this difference was significant, and the effect size being over 0.8 is large. We saw the same with the fastest reaction times. They increased with the original seat, decreased with the enhanced seats. And then we looked at the probability of the lapses, and they increased more with the original seat compared to the enhanced seats. So the only thing we can think of, the only difference we really saw, this is looking at the frequency content of the vibration, or the power from the seat as a function of frequency, is the existing seat had a lot of low frequency energy. So we're wondering if that may affect the reaction times. So I think what I'm going to do is end here, where we have a causality map and we have ergonomics. And ergo, to me, is a 4-letter word, and it also equals another 4-letter word, which I misspell, which is money. And that there is probably billions of dollars in low back pain and millions of dollars that can be saved by preventing accidents. And our problem really is we now procure on low cost. We have producers and consumers, and we have our health and safety department that are aware of tens, potentially hundreds of $1,000s in claims. They aren't really communicating to the C-level, and the C-level is having people purchase things on low cost. Whereas if we purchased an incrementally better seat, I think we could have a substantial savings where everybody would be of greater benefit. So we have to teach our producers and our consumers that purchasing on low cost may not be the most cost advantageous. So with that, I am going to end and take questions.
Thank you so much, Pete, for an excellent presentation. In particular, I love the golf analogy, even though I don't golf. I'm going to jump right into a few of the questions. And the first one is, did the reductions in vibration consider drivers carrying liquid cargo?
That is a great question. We have never really measured any measurements from people carrying liquid cargo, and I understand there's a lot of fore and aft low frequency vibration from the cargo kind of sloshing around front and back. So we have not looked at that. I suspect it is very important.
Okay. Can you comment on health outcomes from using active suspension in off-road applications, if you have any experience with that?
Boy, in on-road vehicles, the frequency of exposure is more high frequency, like oscillating between 4 and 8 times a second. So you don't have to get rid of a lot of displacement. And active suspensions, I think, are very good for that higher frequency exposure. How well they work with lower frequency exposures is unknown. I'm not aware of Bose or ClearMotion that they've done any testing or what testing they've done with kind of lower frequency, larger displacement off-road exposures. I would suspect they could be somewhat successful, but I'm not aware of any results currently.
Thanks, Pete. Have you studied or looked into the effects on worker whole body vibration in the milling industry, such as the grain mill?
Oh, you have some great researchers in Canada that are doing some work, especially at the Laurentian University, Tammy Eger. She's looked at a lot of floor or platform transmitted vibration in people using drills. And there is effects from floor transmitted vibration exposure. And ironically enough, it's kind of more affecting the toes, causing a hand-arm vibration like syndrome. So I'm not aware of any milling work, but the work by Tammy Eger at Laurentian University is probably as close as we get.
Thanks, Pete. Can you say anything in terms of these results being extrapolated to seats in locomotives?
I have not measured vibration in locomotives, but I know it can be a challenge, especially based on the condition of the tracks and things along that line. And I do know that whole body vibration appears to be a challenge for some of the engineers operating vehicles. So I think they could benefit from a suspended seat. And it's just finding out what the type of that exposure is and how it benefits.
Thanks, Pete. You did mention very early on about an operator being too heavy or heavy, and this affecting seat vibration impact. Are you aware of any fitness requirements for operators?
There's a little bit of an irony in both of that. With these suspended seats, actually heavier operators often can be less exposed because the seats are kind of optimized for your heavy operators. So that's something you have to consider is where seats can be problematic is if they bottom out with the heavy operators. But for example, we've done studies with forklift operators where there aren't severe low frequency exposures or undulations, and it's the lighter operators that are higher exposed. And to the second part, I'm not aware of anybody kind of screening vehicle operators and looking at health status or health condition with respect to whole body vibration exposures.
Okay. And are you aware of any follow-up data on the low back pain study?
So we did not do any follow-up with our low back pain studies, and that's probably something that would be beneficial if that would be possible to do more randomized controlled trials with these seats that have differentials in exposures and follow them for longer periods of time. So I think what could be really interesting, and I don't want to sound like the poster boy for the Bose active suspension seat. That study that we did was funded by the state of Washington, and I saw a question, did Bose fund any of that study? And they did not. But I do have to declare that I have been given some gifts from Bose, but that was to do other peripheral related research. But I think what the results do show is if you could substantially reduce exposures, you can improve health outcomes. And I'd love to see in companies that receive this active suspension seat to look at claims 5 years before they got that seat and 5 years after they got that seat to see if there are any effects. So that's kind of a real missing link in this work.
Thanks, Pete. And I think this will be our last question. You did talk early on about the cumulative effect of whole body vibration. The question we have here are the effects of whole body vibration cumulative?
Yes, I think I want to say definitely are. You know, with hand-arm vibration, we had a great indication of the cumulative nature is when they introduced these gas-powered chainsaws. Roughly, there was a 5-year latency between when they introduced these high-frequency vibrating saws and reports of vibration white finger and Raynaud's disease. So there's a real strong link in the hand-arm vibration community. We don't really have that smoking gun with whole body vibration, but you know, I suspect that it is similar, that it's just an accumulation of this micro trauma over time, and it's probably somewhat individual specific as well as being kind of vehicle specific as well, how long that may take.
Thanks, Pete. I'm going to squeeze one more question in, and this is our last question. And have you looked at different seats and chassis, for example, air suspension versus leaf suspension?
I'm sorry, could you repeat the last part, air suspension versus?
Leaf suspension.
Leaf suspension. Yeah, I'm not aware of very many leaf suspension. Well, there are probably some mechanical suspension seats. We have compared mechanical suspended forklift and mechanic and air suspension seats. And what we find out is these mechanically suspended seats are springs. They're very weight dependent. So your exposure is very much dependent on the operator's weight, where these air suspension seats are less weight dependent, where they handle different weights better. So there's less of a differential of the exposure.
Well, Pete, I want to thank you very much for an outstanding presentation and to our participants for their questions and for staying with us. I think this has just been a super presentation, and we still have 94 people on the line, Pete. So kudos to you. Have a great rest of the day and take a nice deep breath.
All right. I thank everybody for attending and listening through the seminar and the opportunity to present.